Everybody, we're going to continue our discussions of alkene reactions in this video. So this one is going to cover halogenation and halohydrin formation. So halogenation, we're looking at adding some sort of like bromine, chlorine, like X2, or we can have some sort of chlorine, bromine, and then water or an alcohol, and we're going to get a couple different products. So we're going to go through the mechanism of this, but I just want to start off with kind of the basic reactions. So when we are forming halohydrins, okay, so that's going to be this reaction conditions. You're using water as a weak nucleophile. Okay, so we're going to see that water or that alcohol add to the better delta plus. And so we're going to think about this very, very similarly to epoxides. And you'll see why I'm saying epoxides in a second when we do the mechanism. But we're going to add the water to the more substituted side. And then the bromine is going to end up anti to it on the other carbon. Okay. So we're looking at this. We're adding these two. So we're getting water on one side and a halogen on the other side. Okay. If we're looking at the reaction to the right, which is just the halogenation, in that case, I'm splitting 1x on each side. And they are going to be anti to each other. Okay, so we're still seeing the same kind of addition reaction procedures here, where we're ending up with something new on each of the two carbons that was part of that alkene. Okay, so let's talk about the mechanism here. So we've already looked at a couple of items where we've seen anti-addition for both of them, but there's definitely some like regioselectivity things that we need to be able to discuss. Also, forgot my little note here. So X is going to equal chlorine or bromine. So F2 and I2, you generally won't see this because fluorine is going to be too violent. So that's just a bit of a out of control reaction. And then the I2 is often low yielding. But you will still occasionally see an iodine halogenation reaction. Okay, so let's look at the mechanism here. So we'll start with the mechanism for the halogenation. So we're starting off with our alkene. And we're going to do bromine here. Okay, so we've got bromine. So together, the molecule of, molecular bromine here at Br2 is a covalent bond, right? It doesn't really have any like polar covalent bonds in it, but the thing that we want to keep in mind here is that it is polarizable, okay? So if this is polarizable, then we can have kind of fluctuations of electron density and where that electron density is being placed. So we could see kind of a delta plus and a delta minus, kind of two poles forming just kind of by that flow of electron density. And of course, our bromine has a whole bunch of lone pairs on it as well, okay? So what we're looking at here is basically we're going to see the alkene come and attack the bromine, okay? Very similar to what we saw with an acid, right? We were protonating those alkenes, except instead of forming a carbocation, we're going to see the bromine attack back, and then something has to give in this whole situation, and then we're going to pop off our other bromide as a leaving group, okay? So that all is going to give us, if we look at the arrows that I've drawn here, I formed one bond of bromine here and another bond of bromine here. So what's this forming is going to be a bromonium ion. Okay, so I've got my bromonium ion here. And now I've got a positively charged bromine. So this by itself just looks horrendous. But this intermediate is exactly where we want to think about this as being very, very similar to the epoxide reactions that we've talked about previously. Okay, because we also formed Br minus in that whole process, right? So our bromonium ion is going to be our electrophile. The bromide is going to be our nucleophile. And we're basically just going to do an epoxide ring opening reaction. Okay, so in this case, it doesn't actually matter which side I attack, and I'll show you why, because I'll do both options and just show you what you get. So I'm going to go ahead and first start by attacking that side and pop that open. Just like epoxides, we're coming opposite our leaving group. So if our bromine is pointing down, the other bromine that's acting as our nucleophile is going to attack from above. And that's going to give us inversion and anti-addition of our two bromine atoms. Okay, so let's look at the same situation, but let's go ahead and attack the other side. So let's go and attack right here, open it up that way. So just like in an epoxide, if we're still attacking opposite our leaving group, which in this case is our bromine, so that's going to have us attacking from the front with this bromide, which is going to push the methyl to the back and then end up with a Br on a dash over here. So the relationship between these two, those are enantiomers. Okay, so I'm just forming a mixture of enantiomers here, and it doesn't actually matter which side my bromine attacks. Okay, so it doesn't matter which carbon you attack, and it's generally going to form enantiomers. Okay, that's definitely something that you need to make sure that you're keeping an eye out for, just in case there's something funky going on. But generally, you're going to see enantiomers come out of this, but not necessarily always. So the other thing we should talk about stereochemistry-wise is this. I just kind of chose to put the bromine on dashes, okay? I also could have formed the other enantiomer of my bromonium intermediate. Okay, so that's going to give me still that same mixture of enantiomers because I can still have these two options and I'm still going to get the same enantiomers here. Okay, so just in terms of our kind of finish up notes for this. So bromonium ion on the top or the bottom of the alkene. Okay, and we're going to say top is going to equal the wedges, bottom is going to equal the dashes. Okay, so we could have either option there. And our bromine, or bromide rather, can attack either carbon. But we're always going to get the anti-addition. Of two bromines. Okay, so let's go ahead and look at the halohydrin formation and see how that compares. Okay, so first step, we've got our bromine. That's going to be completely identical. Okay, and we're going to just make a little note here. This is going to be our solvent. So as soon as something is going to be the solvent, that's going to be a lot of it around. Okay, so we have a large excess of water. Okay, so our first step is still going to be the same reaction with our bromine, because our bromine is the most reactive thing here. So we're certainly going to react with bromine before we react with water. Okay, so we're going to form the same exact bromonium ion. Okay, and just as the case earlier, this is plus an enantiomer. Okay, because I could form the bromonium ion on the top or the bottom. And then I've got water and bromide. Okay, if I'm looking at these two options though, I have a lot more water present than I do of the bromide. Okay, so this is mostly going to be a bit of a numbers game in terms of which one is actually going to be the nucleophile to react with my bromonium ion. So in this case, since I've got a lot more of my water around, we're going to have the water go and attack. So in this case, it actually really does matter which side we attack, because we want to think about this. This is going to have the same regiochemistry as the acidic epoxide opening. Okay, so when I've got an acid and an epoxide and I've got some sort of alcohol or something, we're looking for a really, really good electrophile to react with that weak nucleophile. Same exact thing here, where this bromine, just like when you've got a protonated oxygen, it does not want to be there. That bromine does not want to be positive. It wants to have all of its electrons to itself. So this is really not a happy situation here. So just like in the epoxide, this is kind of pulling away towards the carbon that can handle that positive charge. Okay, so we want to think about it like this. So we're kind of doing the little pull thing where I'm going to have a larger delta plus on one side versus the other side, right? So the more substituted side can handle that positive charge better. Okay, so just like epoxides, we're going for the more substituted side here. So we're going to have our water attack at that carbon, kick off our bromide, and then I've got the water came in on a dash. That's going to push my methyl to the back. And I've got my bromine on a dash. So now I've got this and my bromine are anti to each other. Just like in the epoxide opening, we have a final proton transfer step just to get us to a neutral product here. Ooh, really got away from me. To get to this product, since I also have the enantiomer of the bromonium ion, I'm going to end up with the enantiomer of this guy as well. Where if we had the bromine on a wedge, we'd end up there. Okay, so the things to keep in mind here, again, we're looking for, oops, that's not helpful. So our water or alcohol attacks the best delta plus, which is the more substituted side. Okay, we're still getting anti-addition of the oxygen nucleophile and whatever X group we have. And we want to think about epoxides here. Okay, epoxides in acid specifically. Okay, so I just want to show you what it would look like if we did have an alcohol instead. So let's go ahead and do this with Cl2 and methanol. Okay, so we're looking at the alkene. We've got one side that is more substituted than the other one. That's where our OMe is going to end up. And again, we're going to deprotonate that H. And then we're going to have the Cl on the other side. So this would get you ethers and alkyl halides rather than an alcohol and alkyl halide. Okay, so we will keep practicing this. And as always, let me know if you have any questions, and I'll see y'all later.